Sogrin, is it working now?
Can I share the screen?
Oh yeah, sure. I can hear. I think it's my earphones problem. Yeah, you can try. I already made you a co-host.
Okay, yeah. Let me see. That's my slides. Does it show up?
Yeah. Xiaohui, could you stop sharing? I want to share with an audience with one picture of George. And let's see.
You want me to share it with Sogrin? You want to talk?
Yeah,
okay. Yeah, go ahead.
Yeah, so it's not like, do you want to comment on this picture?
So George is riding a camel and he's lost in the desert. His driver's not there, and he's planning to ride this camel and come back home. That's what he wrote to me, that this would be an exciting trip for him.
Where is this?
He's gone to Saudi Arabia.
Oh, cool. Yeah, let's see.
It can take him years, right, to ride a camel back, right?
Camel cannot swim, so or fly.
Yeah, we need to do Zoom for a very long time.
Okay, let's get started. Okay, hello everyone. Welcome to this week's Crown Seminar. Our first speaker is Xiaohui Chen, who received his PhD in electrical and computer engineering from the University of British Columbia and was a postdoc fellow at the Toyota Technological Institute at Chicago. Currently, Xiaohui is an associate professor of statistics at UIUC, University of Illinois Urbana-Champaign, and also a member of Discovery Partners Institute. He held visiting faculty position in the Institute for Data Systems and Society at MIT in 2019 to 2020. Without further ado, welcome, Xiaohui, and you may want to start your talk.
Yeah, thank you, Zhongren, for having me. And let me just try to maximize the screen.
Yeah, it's good.
Oh, okay. Sorry. Yeah, I was actually a little bit worried about this talk because I'm having a flu right now. So I'm losing my voice yesterday, but now today it turns out to getting better. So I hope the talk will go in smooth. It's a great pleasure to talk about a recent work we have done on neural operators, especially in the optimal transport setting by learning the so-called Wasserstein geodesics. So this is a joint work with my students, Andrew Kyritsis, who is supposed to be here, but I guess he has also a doctor appointment this morning, so I'm not sure he's here. But anyway, so this picture is actually made by Andrew, which is the example for the learned geodesics between mixture of Gaussians. And this code is actually publicly available. So if you want to try this model, you are free to test on this on this code. And in some sense, this work is still ongoing. So I would like to hear some feedbacks from the audience as well. And here's the motivation for this work. And there are actually many modern applications, especially in the artificial intelligence, AI setting, in the modern data science, that can be viewed as optimal transport-driven problems. For example, this is a supply and demand network where you have a few of the cities sampled from different countries, and then you want to transport goods, between different part of the cities. And the question is, how do you, given a cost function, how do you optimally, transport between the cities by minimizing some kind of cost? And this OT problem, is actually, it's a spheric OT problem because this is the transportation on the Earth. And there are other like modern applications in computer visions. For example, this color transfer application. So here, the color transfer basically takes two images, and one is as a reference image and one is as a target image. And the problem is that to mix the two images so that the color style of one image is transferred to the reference image. So here's this is a picture of the math department at the UIUC, and this is a target images which has a different color style. And the idea for doing this color transfer is that in some color space, like in RGB channel space, you basically want to match the color distribution of the reference image and transport it into the target image color distributions, like in this one. So there's clearly the red and the red channel has more like a mass. So you basically want to find the optimal way for transferring the distributions in the RGB space to another distribution in the same space. Of course, you can use other color space which are have a lot of discussions in the computer vision, but this is just the example for using the optimal transport in the data science and the artificial intelligence setting. And for 3D shapes, so this is an example that you can actually transform a 3D shape using some kind of geodesics to a standard simple shape like a unit sphere or unit ball in the 3Ds. And this can also be formulated as the optimal transport problem, and different from the image processing applications. So this domains of this optimal transport problem is actually also an input in addition to the data points that are sampled on the surface. And also for natural language processing here, if we want to do some kind of automatic translations, like here from English to French, this can be also formulated as optimal transport by embedding this sentence, the language, into some Euclidean space. For example, you can do some kind of word embeddings for the English words and also the French words. And in such a metric space, you can choose the appropriate distance measure. And then the next question would be to find the optimal matching for the words so that you can do the translations. After you get the optimal transport problem solved, you can map back to the language space to do the automatic translation. And last but not least, so there are also applications in swarm intelligence, especially in the robotic settings. So one of the kind of the problem that in the robotics is that you have a bunch of robotics and you have a bunch of target locations. So the question is that how do you match the robots to the target of interest in a real-time setting, for example, in this video. Please feel free to interrupt me if you have any questions during the talk. So that's kind of the motivation why we do this problem. And this slide gives you a very quick review of this optimal transport background. It's actually a very old problem due back to the French engineer Gaspar Monge, I guess maybe 300 years ago, maybe 200 or 300 years ago. So the Monge problem is essentially an optimal matching problem. So suppose you have a farms, a bunch of farms, and you want these farms produce the milk, and you want to ship the milk to the artisans to make to produce the cheese. And one of the major problem in this transportation problem is to find the optimal route, to transport the milk to the artisans. And the Monge problem is basically can be formulated as the infinite dimensional optimization problem, such that you have the, sorry, where is my, okay. where you have a source measure, mu0, where in this example, the source measure will be the distribution of the farms. And you have a target measure where it's a distribution of the artisans producing the cheese. And then you want to find the average cost that you transport from the source measure to the target measure. And you want to minimize this average cost over the space of all mapping functions. And clearly, this is a highly nonlinear optimization problem because this push forward operator T push forward this mu0 to the target mu1 is a highly nonlinear constraints. If these two densities have some constraints, you can write this as actually the well-known Monge-Ampere equation, which we know is highly nonlinear. And therefore, to solving this optimal transporter problem is an open problem for a long time. Until the breakthrough that was made by the Russian mathematician Kantorovich in 1940s. So basically, his idea is really simple. And his idea is that instead of directly finding this optimal transporter map T, from the source to target, what if we allow the splitting of the source, masses? So if we allow the part of the fraction of the source measures to be distributed into different parts of the artisans, then basically we can lift this Monge problem into a sort of a augmented space where you're trying to find a optimal coupling, gamma star, and such that you minimize the same cost function. So here the example I gave you is a quadratic cost function, x minus y squared over 2. And you're trying to find the minimum of the optimal transport cost, but you're kind of relaxing the constraints to be a linear constraint, where this capped of gamma, mu0, mu1 is the set of all couplings that you have the marginals of mu0 and the marginals of mu1. And therefore, if you just think about this Kantorovich relaxation, even though this is still an infinite dimensional problem, since you'll find optimal couplings that the distribution is over x and y. But if you think about it, if this mu0 and mu1 are some kind of point clouds, then basically the objective function for a given cost is just a linear function of the gamma. And then the constraints are just the marginal constraints, which is also linear. So in that sense, this Kantorovich relaxation can be solved efficiently using linear programs. And this is actually where the linear programs was initially invented by this kind of optimal transport motivation. And because it's convex, there are many methods for solving this Kantorovich relaxation problem. And it turns out in some cases where for example, if the source measure does not charge a point mass, then basically, if you solve the Kantorovich problem, then basically this optimal coupling gamma will be concentrated in some graph, and that will recover your Monge problems. So that's a little bit of history about this OT problem. And in this talk, we're actually quite interested in the metric space structure about the optimal transport problem. And the Kantorovich relaxation is actually induced a distance between probability measures, which we now call, it's well known as the Wasserstein distance. So if you choose the cost function to be quadratic, then basically that's a squared of the Wasserstein distance between the source and the target. And since this is a linear program, and we can use the standard, duality theory to conclude the strong duality for writing the Wasserstein distance in the dual space, which you simply, split the problem into the source part and the targeted part, subject to the constraint that there is the direct sum of this phi and psi is less or equal than the cost function. So these are well-known strong duality problem. And numerically, in practice, when we want to solve this infinite dimensional problem, what we are given typically is just the point cloud from the measures, right? So the mu0, we have some data samples from this distribution. For the target, we also have some discrete samples, and therefore to solve this optimal transporter problems, there are many kinds of linear programs, finite dimensional linear programs to solve this OT problems. For example, if you just apply the standard interior pointer algorithm without leveraging any special structures, then basically that's super cubic complexity. And there are some specialized optimum matching algorithms like the Hungarian methods, or the auction algorithm, transportation simplex. But all of this, numerical solvers for computing this unregularized OT problems takes super linear complexity in general. And a widely used, variance for more efficiently solving the OT problem is to add the entropy term into the cost function here. If you just look at this, this W2 distance, so that's a direct minimization problem. It's not strongly convex in gamma because it's linear, but you can add an entropy term for the optimal coupling. And that entropy term is the KL divergence, the relative entropy with respect to the product measure of this mu0 and mu1. And that makes the problem, entropic regularized problem is smooth and strongly convex problem. And therefore you can sort of expect a more efficient algorithm for solving this problem. And the most popular, algorithm is called a Sinkhorn, maybe Sinkhorn type of algorithm is basically a matrix, scaling algorithm, which is an iterative algorithm, and at each iteration you compute a sort of scaling weights on the rows and the columns, and you do this until the optimal couplings converges according to certain standard. And this is actually a fast algorithm, not machine learning based algorithm, but given any pair you can compute the entropic regularized optimal coupling. But the problem is that because you're adding the entropy term, so there's a trade-off between the statistical accuracy and the computational complexity. And there are a lot of papers recently going on for studying the optimal trade-off between the statistical and the computational issues, but that's not going to be the focus of our methods. So our work essentially focusing on some learning-based methods for solving the OT problem. And there are some very recent work appeared in this direction. For example, this prime and due methods proposed by Liu is essentially kind of similar to our methods, as I will detail later. So basically leverage the duality, relation between the optimal transporter problem by looking at the optimality conditions, solving the optimality condition using some optimizations. But the problem is again that this only handles a given input, like the initial and the terminal distributions. So for every new initial and terminal distribution pair, you have to recompute the optimal transporter map or geodesics, and this gonna takes another non-trivial optimization efforts to do that. And another direction is appeared in AIMERS this year, trying to estimate the optimal transporter map, which they call this meta-optimal transporter map, by using this machine learning perspective. So this is basically amortized the prediction, for the OT maps. So here the amortized prediction means that you have a bunch of training data, and that training data actually tells you, learn the optimal transporter within this class of the, distributions. And therefore, in the prediction stage, after you train your models on this family of, distributions, then the prediction can be much faster than the traditional OT solvers, which are not based on machine learning. So these are the existing works on solving this OT, problem, in particular the optimal transporter map. But in fact, because of the metric space, structure of this Kantorovich problem, we can actually get richer information rather than just looking at the map between two initial and terminal measures. We can actually learn the whole dynamics between this initial and terminal measures. And in differential geometry language, this is called the geodesic. But because the Wasserstein space is an infinite dimensional space, so it only has the formal remaining structure. So in this setting, so we call it just the Wasserstein geodesic. But it has a similar meaning as a remaining geodesic, which describe the shortest distance between a pair of probability measures. And here's the distance, is quantified by the W2, the two Wasserstein distance, metric we have seen before. So that's a goal we're aiming for. But we are going to do this, using some kind of fluid dynamic, perspective. And this is actually well known. Also in optimal transport, called the Benjamin-Bernier dynamic formulation. So it's again a constraint optimization problem that can express this Wasserstein distribution in terms of some flows. So the objective function is a kinetic energy, integrated kinetic energy, where you look at a squared of the velocity vector field V, weighted by the density flow mu xt, where the flow starts from mu0 and terminates at mu1. And the PDE constraints here in the second line is it's nothing but the law of conservation of mass, which you don't have any escaping of the mass. You don't have the source or sink of the the mass, so everything is preserved by the unity of the mass. So this is a very natural. This minimization is taken over all possible probability measures and all possible velocity vector fields. And the example I show you, the picture, is basically the interpolation computed by the Benjamin-Bernier, from Monge to Kantorovich. It looks like a linear interpolation in some sense, and it's indeed because it's optimal transport. But that's just the example of when you compute, this this BB problem, dynamic formulation problem, along this geodesic. Any questions so far? All right, so here's the challenges we're going to address. So the first challenge is that we want our methods to be mesh invariant. This means that at different time points, or we want to sample perhaps at different resolutions. So this is particularly relevant to this kind of zero short or few short, super resolution problem in computer vision. So here's the example. So we have a low resolution input, like a t equals 0 and a t equals 1. And once we interpolate between this t equals 0 and t equals 1, this mixture of Gaussian, I guess here we have two components mixture of Gaussian in different directions. And in the middle of this geodesics, and we can actually do super resolutions as in this example. And this is actually one of the big advantages for using the dynamic formulation. Remember that if you just do this optimal transport map estimation or learning, the static version once from mu0 to mu1, you're trying to find the Monge map, then basically there's no way that you can do super resolution at the point you haven't observed in the middle. So that's one of the advantages for doing this, dynamic formulation. And the second thing is the amortized inference. So this has already been considered independently by some other authors, as I mentioned before. This is actually also applied in the dynamic problems. Here I just gave you a flavor about, I was initially surprised by, the amortized inference because, in academia, especially for researchers in academia, then our impression is that most of the computational, cost is actually spent on the training, stage. We have a huge amount of training of data. We have, large neural networks. Then the major time, cost is to train such a model. But actually, I look at what happens in practice, especially in reality in the industry. What Facebook, does now, it becomes Meta. It actually processes over 200 trillion of inference per day. So that's kind of data I just grabbed from 3 years ago, 2019, from a report, by Meta. And now I believe that these numbers will grow much bigger than this one. And this tells you that after you train your, the models, it's actually the inference that costs a lot of much more time, in the production stage. If you want really your model to be, to be scaled, to a large scale, then basically you have to have your inference to be efficiently computed and done, perhaps in real time. Because once the model is training, then lots of people is going to using the same model over and over again many times. So this actually requires us to develop some amortized inference that can do the geodesic predictions in real time. And that's also going to happen if you get a new data, you want to fine tune your pre-trained model, because we always get new data every day. So if you have pre-trained model, if you want to fine tune, then basically, you also want this process to be pretty efficient. And therefore, to solve this problem, the idea is naturally to use the operator learning, perspective. And by that, I mean, you're trying to map in your inputs, data, the input pair, which contains the source and the target. And the output of this system will be the geodesics connecting the input pairs, right? So if you can train a model that takes the input pair and learns a highly non-trivial mappings to the geodesics, and then in the inference stage, you don't have to recompute, things repeatedly, right? And the idea is just to use the Benjamin-Bernier. It's very simple based on this fluid, dynamics formulation. And how are we going to do that? The idea is really simple. We just find the optimality conditions, that solve the W2, geodesics. So because this is Benjamin-Bernier, if you just look at how this primal problem is formulated, then that's just a constraint optimization problem. It's actually a convex problem if you reparameterize the velocity vector field, by the momentum, that's actually strictly convex. So you can leverage the Lagrangian, functions by lifting this PDE constraints to the Lagrangian function, where you introduce the dual variables u. And then basically this is a saddle point problem. You minimize over the prime, maximize over the dual, apply the standard arguments, duality arguments, and by exchanging the order of the mean and max, and you can find that the optimal velocity vector field is given by the gradients of this optimal potentials, which is a solution to this Hamilton-Jacobi equation. And therefore, if you're combining this primal feasibility and optimal dual, constraints here with the boundary constraints, you actually can recover the optimal KKT conditions here. And this is a pretty standard in optimal control, problem. So, but here our idea is that we are trying to reconstruct the learning problem of the Wasserstein geodesics by solving this system PDEs, as the optimality condition to the, dynamic fluid formulation of the OT problems.
Xiaohui, I have a question. Can I ask a question?
Sure.
Could you go back to your previous slide? No, previous slide. Yeah, here you mentioned operator learning. So I'm curious, what is the input of your learned operator? So you said, the input should be the pair of the measure at time equal to 0 and the measure at time equals to 1, right?
Right.
So the output of the operator is the whole process.
Yes. So the operator learning, so the input is mu1 and mu0, the two-point measure, and the output is mu xt. The optimal mu xt is not the feasible one; it's actually the optimal one that minimizes the kinetic energy.
Right. So the output will be the time-dependent measure.
Right. Yeah.
Okay.
That's a density flow.
Okay. Thank you.
And because the idea we want to do the amortize the inference, and we think of this operator, this operator is actually, by varying, this input measure, learning some common patterns, and then output the densities rather than just recompute the geodesics for each pair. That's
yeah, got it. Thanks.
Yeah, so that's where this physics informed the deep learning, and I guess many experts in the audience and from, Professor Kyritsis' research group has done a lot of tremendous work on this direction. So this is a scientific machine learning, as opposed to the traditional machine learning or deep learning, which is purely data driven. So scientific machine learning actually using the physics prior, to perhaps reduce the amount of data in order to accurately train the the system. So here's just a baby example I took from somewhere. This is a one-dimensional damped oscillator, and if you just have the data, sorry, I can't find my pointers on my computer. So so on the upper right corner of this illustration, if you just gather a few of training data like the yellowish points, and if you just apply the vanilla neural network, whatever architecture you like, you only learn the patterns, interpolating this data, quite accurately. But out of the range, because there's no data points, tells you the information how to, fit in the curve, then it's very easy to, to make huge errors here. For example, if you just apply a neural network, then this is pretty much, I guess, approximate some polynomial interpolants, and because this is a damped oscillator, so the difference between the neural network prediction and the exact solution we know is actually huge, as you go away from the training data. But what the scientific machine learning with physics prior can actually do this quite efficiently. So the idea is very simple. So you have an underlying model which you assume, which is usually a dynamic system governed by some PDEs. So this time derivative, and then there are some space differential operators on the U function, and that differential operator, depends on some unknown input A. So in this case, the idea is that you can still train this, neural networks based on your training data, but in addition to that, you kind of do some sampling on your space and time domain, and that's what we call the collocation point. And along this collocation point, because you don't have informations, but on the other side, you have the dynamics along this, along these values. So as long as you can fit this, curve with the training data, you can sort of extend in a principled way according to these PDEs to the unobserved, regime of the data. So that's, a toy example of this scientific machine learning. usually works. So basically, with less data, usually it's just the initial, data points or some spatial boundary data points, as the input, perhaps with some kind of, intermediate data, but you don't need that too much. But you need to specify the physical laws, here. And the question to find the solutions of the PDEs as a solution operator, which maps from the input A to the solution. And in our optimal transport problem, we can think about this A is something, is just the input pair, the mu and mu0 and mu1. So that's an input pair which controls how the flow is going. And the dynamics D of A in the general formulation actually corresponds to the two-coupled PDE system. So that's the continuity equation plus the Hamilton-Jacobi equations. So that's a D operator, and the A function is basically mu0 and mu1, which actually together gives the the solution of the optimal flow. So the U in our context is the mu xt. So that's the density flow. All right. So once we understand this, and then this is a classic results of why we can use the neural operator. It's essentially because of this universal approximator theorem. For neural for continuous operators. So there are some well-known universal approximator theorem for functions rather than operators. For example, this in neural network is a universal approximator, right? So and also the polynomials are also approximator. So those are very, very classic stuff. And for nonlinear operators, in fact, there are also results saying that you can approximate any continuous bounded nonlinear operators from continuous function with compact support to another space of continuous function on a compact support. Then we can build a neural network. In this case, it's just 2 layers, or sometimes people call this one hidden layer neural networks that can approximate this G operator uniformly. So this is an explicit, so the proof of the theorem is not constructive, but from the proof you can actually read off the architectures. So there are 2 parts. The highlighted red part is basically cut by Professor Kaniadakis research group for the previous papers. We just follow that. This is a branch network. The branch network using this representation is just one hidden layers where you have linear combination of the input features of the sampled as the input function U, and then you make the nonlinear activations. And then in addition to this branch network, you have the output trunk network where you do the same linear combinations followed by some nonlinear activations, and then you just take the dot product to approximate this G operator. And this is only a non-constructive approach for building a neural network, but it doesn't tell you how to efficiently build a neural network in practice given finitely number of data. And that's where this, in my opinion, this depot nets is a practical way of implementing this universal approximation idea by going through this shallow network into deep neural networks, where you replace this branch and trunk nets by some kind of modern deep neural network architectures. Depending on the problem, whether you have the images or not, so there are many different architectures you can input into this general framework. So that's how this learning procedure is formulated. So specialize this to the geodesic learning problem. So our problem is very natural to fit into this framework. So the solution operator, the gamma deck, takes a pair. The P2 omega is the space of probability measures with the finite second moments. So that pair mu0 and mu1 is the input, and the solution operator throughout the geodesics as a mu-t, which is given by characterized by the continuity and the Hamilton-Jacobi equations. And the practical implementation for the for the dipole nets architecture in the optimal transport setting is that we simply use the unstacked architecture by jointly training this C network, which is the primal network corresponding to the continuity equation, and the H network with the DU network correspond to the Hamilton-Jacobi. And here we slightly make some variations of the universal approximate theorem. Because here we have a pair of input, so mu0 and mu1. Instead of the general framework, you have the single input function A. Here we have the pair. So here we need two branch networks corresponding to mu0 and mu1. So that's the B0 and B1, and the output is still a time-dependent network on the flow. So that's a trunk network. So therefore, for this primal network C, it actually contains 3 networks rather than 2. But since we are characterizing the optimal KKT conditions for the geodesics, we also have the DU networks, which similarly contain 3 networks on the input to two distributions and outputs on the flow. So together, this GeONet contains 6 networks that need to be jointly training together. So here's the picture that highlights the diagram of the whole network. I hope this is clear. And so just to recap, so the input is mu0, and you sample, a bunch of points, and then you throw it to the branch networks, and it output a p-dimensional vector. And on the other side, you have the trunk network where you need to randomly sample some collocation point in order to propagate, this PDE dynamics over the observed, data points. And then you simply take the dot product from this, branch and the trunk architecture. And eventually, the outputs of this GeONet is the C network, the primal network, which depends on X, depends on T, as well as depends on the mu0 and mu1. So it's parameterized by some phi parameter, which is trainable by the standard, AutoGrad's deep learning packages. So the output is a primal network, and in this application, we don't quite care about the output of the trained DU network. But if I have time, perhaps in the end, I will maybe briefly mention some other ongoing project here by trying to utilize the DU, networks, in a different purpose. So the loss function, by combining these things all together, is actually quite natural. So you have the continuity PDE residual loss, by inputting the ice data points, and then you sum over all the training data points in the end. And you have the Hamilton-Jacobi residues plus some boundary residues. So you put them together and minimizing jointly minimizing over these neural networks. So you get estimates. And here, this alpha 1, alpha 2, beta 0, beta 1. These are the tuning parameters. And for now, the first version of this work, we tried a few hyperparameters by Andrew, and later on we have some kind of hyperparameter tuning strategies for automatically selecting these hyperparameters, but it's not quite ready for this talk yet. So these slides summarize the the training algorithm, which is basically end-to-end. You input your training pairs, training pairs, and then you learn a neural network, especially the network parameters phi and psi in the end. So this is a pretty standard end-to-end training by computing this residues and then do just the back propagations on the total loss. So that's that's a method. And to just show you some numerical experiments, so we did some simulations first on the Gaussian mixtures, because Gaussian mixtures is a universal approximator for any continuous densities, as long as you make these components to be large enough. So we sort of think about this is a good like a test bed for checking the performance of these GeoNets. And in a simulation, the training data is actually for the initial data points, we choose like a k = 5, so 5 components. And the ending points is 2 components. This is not quite a complicated Gaussian mixture. It's just kind of a toy example to do some, proof check, concept of proof check. So after training, we make inference by predicting for the new pairs from the same training class, 5 components Gaussian mixture to 2 components Gaussian mixture. And then we compared with this reference geodesics. We don't call it a true geodesics because this is computed by the standard OT solvers called the Python Optimal Transport POT library. And that POT library does is to add the entropic regularization, even though the regularization parameter here we choose is pretty small. It's if I remember correctly, it's 3 times 10 to the power of -4. But still, this is not a true geodesics, because if you really want to compute the true geodesics, you have to go back to the unregularized version, which inevitably will reduce to this linear program, which takes a lot of time to solve on a high dimensional grid. So you see that from at least visually speaking, a contour plot for these predicted distributions of the GeoNets versus this reference geodesics is actually quite close. And this is a table that measures these mean square errors for the example I showed you, but we take like a 50 test pairs. And here you see the super resolution effect. So the training data are just the boundary data, mu0 and mu1 is 30 by 30. And our test data is actually on the 50 times 50 mesh. So we intentionally, raise the resolutions in the test. And here, the GeoNet errors, you see that the benchmark is sort of identity. So training setup is K0 = 5, K1 = 2, 5 components mixture to 2 components mixture. So except the last rule, so the first 4 rules are in distribution errors. So basically, the testing and the training are in the same class, even though K0 could be 3 or 4, but it can be seen as a special and a degenerated case of K0 = 5. So you see that as the identity geometrics, where everything is trivial because you don't actually move in the mass. It's an identity optimal transport mass. So the benchmark for the mean square errors is, for example, T in the barycenter case, T = 0.5. In the first rule is 2.1. So that's kind of the best you can hope, for GeoNets in terms of mean square errors. And if you're moving from this identity to some random pairing, and the errors, of course, will increase, but still comparable on the same order, along these flows. And perhaps you observe that in the last line, there's OOD error. This represents the let me see, out of distribution. So I just copied that table into this slides, the same numbers here. So this, sorry, there's a typo here. So the out of distribution is basically you test the data with a different class of distributions. So here, I think we switched the source and the target for simplicity. So we going from 2 components mixture to 5 components mixture. Previously we have the 5 to 2, but now we're going from a simpler distribution to a more complex distribution 2 to 5. By learning this, but you can of course do other things. And you'll see that we just take like the barycenter estimates, and actually we can do other t's, but the general patterns here is that the errors is actually gets much bigger, actually maybe 4 to 5 times bigger than the in-class in distribution prediction errors. And if you look at this contour plot for t equals 0.5, it's actually quite it's actually quite different for the geodesics computed by the pods. So there's indeed a robustness issues for this GeoNet, and I guess this is a generic kind of issues for learning based methods. There's always especially for neural networks we know that it's not robust, and if you just changing this testing distribution class, then the errors will for sure going up.
Xiaohui, I have a question.
Yes.
Yeah. Could you explain the intuition behind that, the fact that the error for out of distribution prediction, the error at time equals to 0 is much smaller than all the other cases?
Yes, that's actually a little tricky. We're still working on that. So if you look at the loss function here, there's a boundary loss specifically on the loss function. In the middle, actually, it's just the collocation points. There's no training data in the middle. So in that sense, because our training data comes to the boundary constraints, so this will enforce the boundary will be, at least for some hyperparameter tuning setting, with a reasonable beta 0 and a beta 1, this loss function will in some sense dominating, the training process.
Yes, of course. But if you go back to the table and check the error for the time equals to 1, so you also have training data for time equals to 1, right? You have training data for mu1, but mu1 has much higher error than mu0, even though both of them have training data.
Oh, you mean like in the like the second rule, k equals 3, k0 equals 3, k1 equals 2.
No, for the out of distribution.
For which one?
So you see, let me find. So you see here, and here you compare those two. So for
oh yeah. Oh, you mean the I see. So the out of distribution one, right? Yeah, that's actually a good point. I'm not exactly sure this one. Yes.
And that's fine. Yeah. I just want to ask.
Yeah. This
please.
Yeah. I'm not sure if this is. Let's see. It actually looks pretty close to t equals 0.6, 0.75.
Yeah. My guess is because for the out of distribution example that you switch, like in the training you don't have k1 equals 5, right?
Yes.
The k1 is much smaller, but actually in the training you have k0 equals 5, which is may contains the case.
Oh yeah, that's kind of in distribution, right? So
right. So it is in distribution for mu0, but out of distribution for mu1 and also for the joint distribution of mu0 and mu1. So that's a good point. Yeah, it could be, and perhaps we can check later. If we also change mu k0 to something like a 6, maybe the other boundary is also getting much worse. Right. Yeah. Thanks.
Yeah. Thank you. That's a good suggestion. Let me see. Can you see the runtime comparisons slides, I think.
No,
Nice.
no, we
Yeah.
it's still
Kind
the
of-
mean square arrows.
Oh,
slide.
resume share. Yes. So this one, can you see?
Yeah.
Okay. Yeah. Yeah, the screen share is paused. So this is just kind of unsurprised, runtime comparison with POTS, because POTS is just a non-machine learning based methods. For every pair, you have to recompute. So for this GeoNet, it's kind of a linear path of the neural network for each new training for each new pairs. So we plot this runtime versus the amount of data, the data size of the, actually this is the testing data size, on the log scale. So you see that the slope of these pods and the GeoNets are actually different on the tails when the data size are getting larger. So this actually suggests that if you get these linear patterns with different slope, then basically GeoNet is faster than the pods by orders of magnitude. The exponents is different. So that's kind of not surprising because of this, amortized inference nature. Of course, the price you pay is the training time for the model. But once this is done, you can either make the inference, or you can just fine tune on the pre-trained model. So that's how typically things works. Lastly, we apply this to the SVPEN data. So this is a 32 by 32 colored image, and the color space here is RGB input to the GeoNet. So instead of distribution for each channel, we normalize this as a distribution. Here it gets 3 channels, so you get 3 distributions, for each images, and then in the end, we, after individually learning this, this is not a ideal, modeling. We are still working on the joint, space, as I mentioned in the beginning, but as the kind of example to demonstrate, we separately learn this geodesics in individual channel, and then in the end, we combine together. So we combine with the POTS reference, and the learned geodesics is shown on the left. It's hard to say. It may be slightly better because SVPEN is really a low resolution image is just 32 by 32. So super resolution in some sense, it's hard to do on this data. Currently we're trying to testing on some high definition, high resolution, data sets, but the issue is that we need to substantially change the model architectures rather than just using a vanilla artificial neural network. In the current context, we have to use some kind of advanced versions of the convolutional neural network. Actually, we have some preliminary network which can improve, these results, but I didn't include it in the talk slides to handle images. And for the super resolution on the right, so you see these are 6 images, and on the left, on the first and the third row, that's the original SVPEN images on my scale. So you see that the resolution is pretty low. And on the fourth and second and fourth rows, so that's slightly high resolution. You can see that it's better than this original SVPEN, but still kind of blurred. I think that's maybe because of the the data itself, because of low resolution, as well as the model architecture can be improved, as well. Quantitatively, we also collected this GeoNet errors. Again, compared with the reference geodesics computed by POTS, and we took some identity pairing, meaning that the input and output, geodesic input and output images are the same, and you don't have to compute anything, and you just run this this GeoNets and compare with the identity function, integrate. So that's errors. And random pairing is kind of slightly harder, than this benchmark. So you see that errors is actually the errors are increasing, but still comparable to this to this baby example, identity pairing. So that's what we got. And so far, you notice that we actually solved this Benamon-Bernier problem, which is unregularized, OT problem, dynamic formulation. As opposed to that, the pods, no matter how epsilon small, is still approximate geodesics. So here I would like to emphasize that GeONet is actually can solve this unregularized problem, machine learning way. But it also can solve this entropic regularized versions because this is closely related to this Schrodinger bridge problem, where you can also formulate as a dynamic, problems, similar as this unregularized version, which is Benamon-Bernier. So here you basically adding noise, to the path, but meanwhile still minimize the kinetic energy. And the only difference in the primal problem is that you have a entropy term comes into the continuity equation. So this PDE constraints in the ER GeoNets is actually adding epsilon entropy term. So that's a Laplacian of the mu, gradient of the log, gradients of the, divergence of the gradients of the log of mu, these things. And you can follow the same kind of Lagrangian arguments, to write down the due problem, which is regularized, Hamilton-Jacobi equation in a similar way, subject to the same boundary conditions. And there are many kind of classic results saying that if you're letting this noise epsilon down goes to 0, then this optimal entropic interpolating flow is actually getting closer, converges to the solution of the Benamon-Bernier problem in the sense of the vanishing viscosity, solution. So very classic in the PDE. So this actually tells us that the GeoNet is actually can be modified to be comparable, in a similar framework as the the standard OT solvers with this entropic regularizations. So it's pretty flexible, formulation. And to conclude, I just want to mention some kind of ongoing work we're currently dealt with. So here we presented a new framework for learning this geodesics, but currently we don't have some statistical error analysis for the learned geodesics. So the next step would be to quantify the rate of convergence, or maybe the first step, the consistency about training the GeoNets, and to get some error bounds for the generalizations. And the second, you see that the way we do this is actually using the fluid dynamic formulation, which have a differential geometry, kind of interpolation, in the Wasserstein space. Because that's a formal, remaining structure there, so we can do sort of remaining metric learning, which has a lot of applications in computational geometry. In essence, the learning the Wasserstein geodesics is kind of similar to learning the metrics, right? So if you can learn these tangent vectors, the optimal tangent vectors, then basically, which is actually part of the, the solutions in our framework, you can do sort of, metric learning problems, as well in the Wasserstein space. And we can also do inverse problems. For example, one of the projects we have been doing with some students here is that we want to do kind of trajectory inference using optimal transport. And the problem is very simple. You observe actually a snapshot of the data at different time points. And then you're trying to reconnecting this, images into sort of movies. And in inverse problem, people call this trajectory reconstructions. Of course, this is in general, you define a problem because there are multiple trajectories can give the same set of marginals. But if you impose to certain kind of physical constraints or maybe physical induced constraints, then this problem can be regularized to be well-posed problems. One of the reasonable constraints is the optimal transport constraints. Basically, if you're moving from one images to another images, you want to minimize the cost. And this is actually quite popular in some scientific domains, like in biology. People are trying to study, the developmental trajectory patterns, for stem cells. And this kind of single, RNA, single sequencing RNA techniques, single cell RNA techniques actually, can only measure the snapshot, because once you apply this technology, the cell just die, destructed. So you don't observe the subsequent trajectory patterns. So people actually measure certain snapshot of, data, and they are interested in the question, is the stem cell going to the skin cell, going to the neuron cell, going to the muscle cell, question like that. So this is a pretty much trajectory, construction problem, inverse problem. And one of the dominating, very popular assumptions in this developmental biology is so-called a Vertigan, landscape, where trying to minimize the amount of mass to move in some gene expression space, which is a high dimensional space. But if you want a gene to express in a stem cell different from this skin cell, you're trying to minimize the cost in certain high dimensional space. So this is a natural problem for applying these GeoNets to learn this trajectories in some biological problems. And also, for generative modeling, this is also doable, because this generative modeling is very popular in AI right now, like the diffusion models, the GANs a few years ago. So this GeoNets is actually can be applied where one end of the distribution is is a noise, is a prior distribution, which is easy to sample, and the other end is the targeted distribution, which may have some, in the image case, which may have some kind of manifold hypothesis. So in this case, it's actually going from learning the Wasserstein geodesic problem to the unpaired setting, because it doesn't make too much sense to connecting noise to the actual images. It's actually trying to learn the dynamics in the unpaired setting. You have a distribution of the noise, you have the distribution of the images. How do you connect them in, for example, cost efficient way? So this can be also adapted to this generative modeling. And I believe that a few years ago, some researchers from Professor Kaniadakis' group has done some similar work, using optimal transport for this setting. But using GeoNets can be another alternative, for achieve this purpose. And finally, we're also doing something like a computational geometry and a graph data. These are 3D and 2D data, but different from images. They are not like on a fixed grid. So you have to take on the domains as also the input into optimal transport problem. So there are many of other issues that we're currently dealt with. So that's all of my talk. Thank you very much for inviting me to present the work, and any questions, welcome.
Thank you, Xiaohui, for your wonderful presentation. Do we have any questions for our speaker? Xiaohui, I have one question for the last slide of your presentation. So, are you familiar with I mean the next steps? So for the computational geometry, have you ever heard the point net or the generative point net?
A point net, you mean?
Yeah, point net. You can search on Google. It's I think it was proposed a few years ago, dealing with the 3D, 2D shapes. So instead of the field, they focus on point cloud.
I see. Yeah. I Googled that. I saw this, but I didn't realize, these things.
Yeah, it could be, applicable to your problem.
Yeah, that's a good suggestion. I'll definitely take a look at that. But what I realized the most one of the most work in terms of generative modeling is the potential flows, developed by, I guess, the previous students of
Yeah.
yeah.
Ruiyuan, yeah.
Yeah. Yeah, that's kind of similar ideas, but still, that's before the diffusion models, and I guess the part of the work were still relevant to the GANs formulation using the minimax formulation in somehow, if I remember this correctly.
Yeah. You're right.
Yeah. That's a good suggestion. I will take a look at that. But this generative modeling is really a topic thing, and I think different from the optimal transport perspective, there are other people recently I have been aware of using kind of the physics constraint prior to better learn the generative model. One of the work come from MIT group using the so-called Poisson equations, in the static electric field. So you that's a kind of stationary distribution is governed by this these Poisson equations, right? So
yeah, could you share with us through the chat? Maybe do you have the link to the paper? Could you put it in the chat?
Yes, Poisson flow.
Yeah, thank you. Yeah, Xiaohui, we may move to the next talk because of the time limitation.
Okay, yeah, I'm just putting this here, and then I'm done. Okay.
Oh, I see. Thank you. Thank you for sharing this with us. Okay, so we move to our second talk, and our second talk is given by Ruiyuan Kang and his PhD supervisor Dimitrios Kyritsis from Khalifa University at Abu Dhabi. Ruiyuan is a fourth-year PhD candidate in mechanical engineering. He received his bachelor and master degrees in aerospace engineering from Honors College, Northwestern Polytechnical University, China. Currently, he is working on AI-assisted quantification of flare and fugitive gas. He's interested in adapting and developing machine learning algorithms for specific scientific or engineering research needs. Ruiyuan, are you there?
Yeah, I'm here. Yeah.
Oh,
nice to see you.
Yeah, nice to see you too. Could you try?
I think Dimitrios.
You're here, right? You're here as well, right?
Yeah, I think Dimitrios is already here. So
yes, I am
to say
here.
hello.
I am here.
Yeah.
Great.
Which one of you wants to start first?
Let me go first for a few minutes and just explain for the group what we are doing here in Abu Dhabi.
Yeah.
The first thing that Zongren I would like to do is apologize from you and everybody present. I do have COVID as we speak. So if I have a little bit of sneezing or coughing, please excuse me. All right.
Yeah, it's all right.
Now, so first of all, I would like to thank Professor Karniadakis and you, Zongren, for this very distinct honor of this presentation. Can you see my slides?
No. Did you share it?
Yeah, 1 second.
Sure.
All right. How about this one? Now?
Yeah.
Yeah, I can see it. Yeah.
All right. As I said, I would first of all like to thank the Brown Group for the distinct honor of this invitation. What you will see today is part of the work that we are doing here in the context of carbon neutrality, and in particular within the Research and Innovation Center for CO2 and Hydrogen. We call it REACH, which when it comes from the Middle East sounds like a pretty weird acronym, but really does not have to do with how much we are endowed, but rather with the ideas that we would like to pursue. My name, as Zongren said, is Dimitrios Kyritsis. I am the chair of mechanical engineering here, and actually also the deputy director of this center that is focused on carbon neutrality. What I would like to talk to you a little bit about is this carbon neutrality research that we have here, and then show to you how machine learning came into the game before I pass it the floor to Ruiyuan, who knows everything about machine learning, and we'll pick it up from there. So basically, we have a center that has two main branches. One branch that relates to CO2 capture, separation, and then utilization, and then to hydrogen, which is first production and storage, and then distribution and utilization. Very rich activity in all of these four themes of our center. And if I could talk a little bit about our infrastructure, this involves some really spectacular experiments. So here, what you can see is we have one of the largest experimental solar thermal facilities in what we call our Masdar campus. And then our research entails everything from advanced materials research, photocatalysis, biochemical processes, supercritical CO2, computational labs, and then all these microscopy techniques that we are going to talk about in a few minutes. The center involves 19 faculty from several departments and 60 more research scientists and postdoctoral associates, as well, of course, as PhD students like Ruiyuan. Now, the areas of expertise in CO2 relate to traditional and novel solvents for CO2 capture. For obvious reasons, we have a very large interest in sequestering CO2 in rocks that come from depleted oil fields. Then we are working very intensely into the utilization of CO2, as you are going to see in a minute, with a particular focus in converting it to synthetic fuels. And then something that does relate with our AI effort is multi-scale modeling of the complicated processes involved in both capture and utilization. The expertise that we have in hydrogen focus mainly around green and blue hydrogen. Notice there is, of course, very large research internationally in getting hydrogen out of water. We additionally have work from H2S splitting. Why? Because this H2S is here in huge quantities in the natural gas wells from which our natural gas is being extracted. Then there is also work in hydrogen transportation and fuels like ammonia, and again, multi-scale modeling work of all the processes that involve hydrogen, catalytic and non-catalytic production and utilization. Our center has been very active in terms of both attracting industrial support and interest from the international carbon neutral energy community. In fact, short before the pandemic, we were able to have this very nice workshop here with our colleagues from Japan, who are pioneering the hydrogen effort internationally. Now, you may be wondering, where does AI come in all this picture? Now, first of all, and this is something that Ruiyuan will not be talking about today, I understand, is that these processes involve very, very complicated networks. You have all heard of electric cars and electric infrastructure. It is becoming increasingly obvious that it will be electric, but not in the way that you think. So basically, what emerges as a very important storage medium that can secure seasonal and long-term storage in a way that batteries cannot is synthetic fuels. The idea is the following. You have your renewable sources here, and this is something that I got from a paper, pioneering paper by Steve Verhelst back in 2014. And then you produce your electricity, and basically what you do, any excess of this, you use it in order to produce fuels like hydrogen, and then by recycling the CO2, carbonaceous fuels like light alcohols and CH4. So a first thing is to make all this system work in an efficient way, and in a way, of course, that secures the appropriate treatment of the intermittency of the renewable energy sources. However, another area, and this is where I will pass the baton to Ruiyuan, relates to the diagnostics of all these processes. And this actually brings me, I don't know if George has had the opportunity to join us, to the way that I met Professor Karnadakis. I have to say it is approximately exactly 30 years ago. So when I was a graduate student, George had kindly offered me a position in his group. He was a junior faculty member then. But I told him very politely, Professor, this is a great honor, but I would like to do something experimental. So I went ahead and did experimental work like what you see here. We shone a laser sheet into a practical engine cylinder, and we got spectral images. This is from a phenomenon that is called ordinary Raman scattering or spontaneous Raman scattering. And we were trying to measure fuel concentration from these images. These images come, you know, with a lot of noise, mainly because you are chasing a very weak signal. Spontaneous Raman produces signals on the order of 100 photons per pixel, which means if you forget anything else, your shot noise, the noise that is imposed on you by quantum mechanics, is at least 10%. This gives results that are very difficult to quantify, like you see here, or these results from a similar experiment by Professor Long at Yale. So the classical calibration methods with which I spent my 5 years in the PhD was we would do calibration experiments, measure the intensity of the signals, and then try to, for example, measure the mole fraction of methane in here. And here I have, you see the several areas from 0 to 16 and then 16 to 32, all the way to areas that are essentially pure methane. Well, too bad that in order to usefully control or even assess this process, you need an accuracy here that is not on the order of 15 or 16%, but rather of 1%. So basically, my own PhD thesis that used the classical calibration methods of the time yielded a negative result. However, I have always had in my mind the question, can these spotty, noisy, spectrally resolved data that have all these peaks and spikes be really better than what they show? Who would know that 30 years after we met, George's and Brown's work would pretty much set the stage in order to answer this question. And through a collaboration with my good colleague from electrical engineering and computer science here in Khalifa University, Professor Panos Latsis, who I understand is in the audience, and our brilliant graduate student, Ruiyuan Kang, we were able to, I think, find out some really good stuff relating this. Basically, it was found mainly by Ruiyuan and Panos, and now Ruiyuan will give us more details. Ruiyuan, the floor is yours.
Thank you, Dimitrios. Thank you for excellent introduction. Okay, let me share my slides.
Dimitri, you need to stop sharing, and then Ruiyuan can share. Yeah.
Okay, good. Minute, I want to. Yeah, can you see my slides now?
Yes.
Okay, fantastic. Good afternoon, everyone. My name is Ruiyuan Kang, a fourth-year PT candidate at Khalifa University. And first of all, I would like to say thanks to George for his invitation, and it's a distinct honor for me to present here. The title of my presentation today is Self-Validated Physics-Embedding Network, SVPEN, a general framework for inverse problems. This work has been done under the mentor of Professor Dimitrios Kyritsis and Professor Panos Liatis. So in today's talk, I will first quickly go through the background of the topic. Then I'll move to the introduction of the algorithm SVPEN and proceed with some applications of SVPEN to show its characteristics. And finally, I'll end today's talk by a short discussion and summary. So let me first introduce what is forward and inverse problems. Well, for the forward problem is from a state to estimate its corresponding observation. This kind of problem is often well posed and has a good theorem or model to link. Well, the opposite side is called the inverse problem. So it's from the observation to estimate the potential state that caused this observation. And this kind of problem is often ill-posed. What I mean is one observation may have several potential states. So let me give some concrete examples. The first example is just like what Dimitri said before, is by shooting a laser to the gas cloud, and you can record the signal from another side by spectrometer. Then according to the concentration of the gas cloud and the temperature along the light path, you can get different molecular absorption spectra. And this is the forward problem. The inverse problem is from this spectrum you acquired to estimate the concentration and the temperature. The second example is about that if you know the design parameters of the aero engine, basically you can estimate its performance on an aircraft. So this is a forward problem. The inverse problem is from the requirement of performance of aero engine to design an aero engine. The last example is about electrical impedance tomography, that if you have a material or surface that possessing a conductivity distribution, by surrounding it with some electrodes and apply current to a pair of electrodes, then you can measure multiple voltages from other electrode pairs. This is the forward problem. The inverse problem is from the measured voltages to reconstruct the conductivity distribution. So how to solve all these inverse problems intelligently? Well, the first method is currently very popular and common. It directly maps the observation to the state by a machine learning model. And this method is named as inverse function method here because the machine learning model basically approximates the inverse function of the forward model. It's pretty efficient because there's no iteration inside, and it could be accurate if the test samples and the training set satisfies the independent and identical distribution assumption, which is known as IID. As for the ill-posed condition I mentioned before, some people use the mixture density network to tackle, but more people, they will use the regularization terms to directly reduce the solution space. The second method I named it as the optimization method. So for this method, they do not directly map the observation to the state. Instead, they will iterate the state to find an observation which is similar, most similar to the given one. And there are two sub methods. One is named the surrogate model-based method here. So in this method, they will use a machine learning model to be the surrogate model of the physical form model. Therefore, they can do very quick iteration. Another method is named as physical model-based method here. Actually, I found it from this paper, Deep Feedback Inverse Problem Solver, that they do use the physical form model in the iteration process, but they use another network to get the update of the state. This kind of idea is pretty similar to the idea in meta-learning that's known as learning gradient from gradient. However, because all these methods need to be trained in advance, so this will bring inevitably some limitations. One, machine learning can approximate, but can hardly be exact the system, because no matter how we train, we still have the loss. And the data set we collect cannot cover all cases, especially for scientific research. Second, machine learning is blind in training, especially for supervised learning, because it only listens to labels in the training process. And in the deployment, the machine learning model is unsupervised. What I mean is the quality of the output of machine learning models are not assessed, basically. But the data faced in the deployment is dirty, deceptive, etc., which is summarized by Dr. George as 5D law. So this indicates that machine learning models cannot assure to always work well in deployment. And this is exactly the thing that people tell me when I try to sell some ideas to them. When some audience with very strong science or engineering background, they will tell me that, well, the machine learning you tell about is just kind of boring fitting games, and they do not believe it can always work. The only thing they can believe is experiments or beautiful and rational physical models. So this kind of challenge or embarrassment is exactly the motivation I try to develop SVPEN. So what is SVPEN? Well, in the training process, there's no difference between SVPEN and conventional supervised learning, but we still need a data set to train a state estimator to estimate state. But in the deployment, we'll add a physical form model to the estimated state, and then we can reconstruct the observation. By some error calculation function, we can calculate the discrepancy or difference between the given observation and the reconstructed observation. Therefore, we will get some error. If the error is smaller than a threshold, we will accept this error and regard it as physically reasonable. However, sometimes the error is larger than the threshold. How to deal with that? Well, the intuitive idea is, can we backpropagate the error to get the update of state estimator so that the state estimator can generally gradually find a way to provide a proper state that decreases error to less than the threshold. However, the problem is not all physical form models are fully differentiable. Sometimes it's just because it's too complex to calculate the gradient, or it's annoying to calculate gradient. So it means this backpropagation routine is broken. Our idea is, can we use another network to bridge the state estimator and the error, so that we introduce the error estimator here, that to mimic the error from the given observation and the estimated state. So in each iteration, we'll update the error estimator by this loss function, and to force it to learn the way to mimic the error. And after that, we'll update the state estimator by this loss function, so that we can force state estimator G1, to find a proper state to minimize the estimated error provided by G2. And by such a updated way, we can let G1 to learn the adaptation of a state from the online feedback of error. And with some iterations, we can eventually find a state that provides an error smaller than the threshold. So this kind of architecture looks like a GAN or actor critical reinforcement learning, well, they do have a lot of similarities, but they also have a lot of differences. I just write all of these things in the preprint, so you can check. The most intrinsic one is this kind of architecture is used in deployment rather than training. Although the idea is pretty simple, we do have a lot of special designs to make it works. So as for the aspect of error and update design, we do use the regularization terms to complement the error calculation function, so that by using regularization terms, we can avoid the ill-posed cases, provide actual guidance, and also reduce the solution space, etc. It has a lot of usages. Besides that, we use a tag called delete update, that we will update error estimator multiple times before updating state estimator once. The reason I do so is because only if the error estimator found a correct direction to update, then the work of state estimator will be appreciated. So this is also known as choice is more important than endeavors. But we do not update error estimator in a blind way, because a slight change in learnable parameters in error estimator may cause a significant fluctuation in state estimator. Therefore, we only update G2 once the loss of G2 is larger than a threshold. And this threshold is named as activation energy here, which is a concept borrowed from chemistry. Besides, we also use the cosine annually warm restarts to get rid of the local minimum, because error space is non-convex in most of the cases. In addition to that, we also use the tag called ensemble of error estimators, because when you check, you will see the purpose of G1 is to minimize the error. So in order to stimulate its update, we do not use a single network to estimate error, but use multiple parallel networks to estimate error, then use a maximum of them to be the final error estimation. So in this adversarial update way, we can force G1 to update very actively.
Ruiyuan, can I interrupt?
Yeah, please.
What is the intuition behind using the ensemble of the error estimators?
Sorry, I didn't get it.
I mean, what is intuition? No, sorry, intuition for using multiple networks instead of single.
Yeah, because you can see from this that if you know adversarial, I think you know the gun, right? So actually the training process is pretty adversarial. So the G1, if we use only a single network, the G1 will find a direction that found a trick to get a very small error. But if we use multiple, and we always use the maximum of them, so that we will let G1 to update very actively. And by this way, we just want I don't want G1 to stay in one place. I want it to run and to find the active direction to update. That's it. Yeah.
How many G2?
Yeah, that's a question. That's a good question. In fact, we only use two. We only use two because considering the computation efficiency, well, you can use a forest of networks, but we are not rich, although we're from a rich group. So we only use two. Yeah.
So does it improve it?
Yeah, it improves a lot. I have done the
okay.
Yeah.
Thanks.
Thank you. Yeah. Okay, let me continue. According to the error function design, the actual error we calculated is always non-negative. So in order to reflect this property in the output of network G2, we add the sigmoid activation function at the end of the output of network G2. Therefore, we can make the output of G2 is non-negative, and we also times it with coefficient k, so that you can zoom in or zoom out the error range. And we also learn some tricks, learn some skills from the reinforcement learning, because if you only use the current estimation to update G2, it's pretty stochastic. So if we can use the samples from some replay buffers we can stabilize the optimization and accelerate the convergence. And here we use two buffers. One called the random walk buffer, that we just randomly search sample the states from the physical domain of the states, and then calculate the corresponding error. And another one is called the in situ exploration buffer, that we just add some noise to the current estimation. So then calculate the corresponding error. So these two buffers works just like the cos Fox knob or fan Fox knob of the microscope. And in addition to using the current estimation, by using samples from these two buffers, we can let G2 to sense both the global distribution of the error and also the detailed regional distribution of the error. Well, there are also some optional designs. The most interesting one is we can also pre-train error estimator because we have a training set for G1. So we can sample and pair the observation or state from this data set, and then calculate the error by the error calculation component. Then we can train G2 in a supervised way. And this kind of pre-training, very similar to energy-based model, or you can regard it as a variant of contrastive learning. So let me summarize the flowchart of SVPEN. For given observation, it will first go to the inverse function mode. The state estimator G1 will give first a quick estimation of state. If the error calculated is smaller than the threshold, then we will regard this estimation is physically reasonable and accept that. However, if the error is larger than the threshold, we will introduce the error estimator G2 and let it to bridge the state estimator and the error, and also feed back the information of the error to the state estimator. And with some iterations, we can find a state that leads to an error smaller than the threshold. Because we always use this physical evaluation module to be the only referee, so the acceptable state estimations are always physically reasonable. And this kind of organizations also make SVPEN be a reconfigurable model. What I mean is you can change, update, or replace physical for the model or error calculation component at will for the purpose of solving different inverse problems. But you don't need to retrain or change error estimator because the optimization mode will find the proper state to lead to an error smaller than threshold. Besides, in some cases, we do not know the actual observation, but we know some properties or preferences of the observation. So just like, I do not know Dr. George before, but I have read his papers and I know what he has done. So if you have a way to embed this kind of information, the properties or preference of observation into error calculation component, then you can also use the optimization mode to find a proper state. This is named as the extended optimization mode here. So as a candidate for Doctor of Philosophy, I would like to talk some philosophy here. For ordinary inverse function solution, you can regard it as a single yin or single yang in Chinese philosophy. I think Zhongren is pretty familiar with these things. And then it's a open loop and a single way or single shoot solution. But in SVPEN, by introducing the physics-driven fault model, we close this loop and allow it to iterate inside and reach the status of Taiji, which means in Chinese is harmony, self-contained, or self-consistent. Perhaps this figure is more intuitive that the two fishes are chasing each other, which means the iteration and they construct a closed loop. Now let me show you some applications. The first application is about molecular absorption spectroscopy. As I mentioned before, the forward problem is from the concentration and temperature to generate the spectrum. The inverse problem is from the spectrum to estimate the temperature and the Moore fraction. So this is exactly the task for the G1 state estimator. And we also prepare a data set for training G1. The substance we search here is carbon dioxide. The temperature range is 600 to 2000 Kelvin. And the mole fraction range is 0.05 to 0.07. So the spectrum we generated is in this waveband, and the resolution is 0.1 centimeter minus 1. So we will generate a 200 dimensional spectrum. And the physical model we used to generate a spectrum is called HiPi, which can simulate a spectrum in a very accurate way because it considers a line shift and a line broaden effect in equilibrium or non-equilibrium states. And also it can simulate the instrumental slit function. Besides, it's pretty powerful because it can simulate the transmitting spectrum, observation spectrum, and the reading spectrum, etc. The dataset coordinated with this platform is HiTemp database. This is a variant version of HiTrain database. It's designed for the simulation for spectrum at high temperature. And this database is well recognized by the community and has been applied to many fields, as you can see the citation here. So what I want to say is both tools here are validated by the community and the experimental data, so they are trustworthy. In total, we have 10,000 samples, 8,000 for training, 1,000 for validation, and 1,000 for test. So the HiPi is directly put in the physical Ford model place, and it will take the estimated state as the input, the estimated state as the temperatures and the mole fraction, and then it will feed back with a reconstructed observation, which is a spectrum. In addition to HiPi, we also use another alternative called Redis, which is much faster in computation, and it has some slight difference compared to HiPi in simulation. So this kind of difference in simulation or mismatch will introduce some very interesting phenomena, and I will show you later. And as for the error calculation function design, for the part of discrepancy between observations, we do not use the ordinary Euclidean distance. Well, instead is paired by this potential well, we designed this logarithm-based error function that the closer the reconstructed observation to the actual observation, the quicker the discrepancy drops down. So by this way, we can attract G1 to iterate to this direction. And we also designed the regularization terms to the physical domain of state. The information delivered by these two regularization terms is that if the estimated temperature or the mole fraction is outside the physical domain, then the actual error will be generated. So the final error is the sum of all these three terms. Here, we do not set a small weights for the regularization terms because we want to construct rigid constraints.
Ruiyuan,
for the net,
Ruiyuan, may I interrupt? Yeah, I want to ask, so what is this HiPi, this part? So is it able to, are we able to do back propagation through this one?
No.
Oh,
yeah. That's why we need the error estimator to help to Skype this.
Yeah, that is why you can use this one to have the G1, right? Because you cannot do back propagate.
Yeah, exactly. And also I'm a lazy guy, so I don't want to calculate the gradient by my hand.
I see. Yeah, great.
Okay.
Thank you.
Yeah. And then as for the network configuration, the state estimator G1's function is to estimate the concentration temperature from the spectrum. So here we just use a very ordinary or classical VGG13. And because we are processing the 1D spectrum, so we modified the 2D convolution layers into 1D convolution layers. And we also remove the bench normalization because we are processing a regression task. At the end of the convolution layers, we add a adaptive maximum folding so that G1 can process different dimensional spectrum. As for G2, its function is to estimate error according to the given spectrum and estimate the concentration and temperature. So here we just borrow the convolution layers or encoder from G1 to extract a feature from the spectrum. And then we use some dense layers to decompose the information inside the concentration and temperature. And then by combining the features from two branches, we will estimate the error. So after the training with the data set, we test the SVPEN with the samples from a test set. So you can see it works well. After all, it follows the IID assumption, and the estimated temperatures and morphorations are exactly overlapped with the ground truths. However, we do not have this kind of ground truths in deployment. So the way we can assess the quality of the estimation is to reconstruct the observation, to construct the spectrum by the physical Ford model. So if we use HiPi as a physical Ford model, the reconstructed spectrum is overlapped with the given spectrum. But if we use Redis, because of the simulation difference, the reconstructed spectrum is obviously different from the given spectrum, and correspondingly, the error calculated for the Redis is much higher than the error calculated for the HiPi. And this phenomenon tells that the real boss in SVPEN is physical evaluation module. So if we test the SVPEN by a sample from HiPi, but we set Redis as a physical model, so you can see there are some mismatch happen. And for the inverse function mode, G1 gives a very accurate estimation because it has been already trained by the samples from HiPi, but the error is pretty high because the assessment is done by Redis. So it moves to the optimization mode, and with some iterations, the error is decreased. However, the estimate of temperature and morphoration are far from ground truth. And this kind of phenomenon is pretty interesting, but also physically reasonable. So if you treat the sample from HiPi as experimental data, then the mismatch between HiPi and Redis, you can regard it as uncertainties between experimental data and modeling. So this kind of phenomenon you will see in every day's comparison between simulation and experiment, that this mismatch or uncertainty plays like a C-hole. It will lead to a high observation error or high state error, but it won't never disappear. So, however, we have to admit that this final state estimation is physically reasonable because it leads to a spectrum that most similar to the given spectrum. The problem here is not caused by SVPEN. In fact, the problem here is caused by the low fidelity of modeling. What I mean is the mismatch between HiPi and Redis. And the common machine learning model or the ordinary machine learning model is pretty vulnerable in generalization or extrapolation. So if we test the SVPEN with the outlier case that the spectrum is generated by the temperature of 3000 Kelvin and morphoration of 0.03, you can see this this setting is outside of the range of training samples. So for the inverse function mode, G1 cannot give a proper estimation, but with the help of optimization mode, it will gradually converge to a physically reasonable estimation. And also, we test a sample from another waveband. In fact, it's twice larger than the ordinary one or original one. So this is a totally different task. Also, we use the maximum adaptive polling at the end of the convolution layers. G1 has never learned such kind of knowledge, so it cannot work well in the inverse function mode. But with the help of the optimization mode, we change the physical Ford model to this waveband, and it can converge to a physical reasonable estimation. We also test the SVPEN with a sample from emission spectroscopy. Emission spectroscopy is thoroughly different from observation spectroscopy because here we do not have the laser. So we do not get the baseline intensity from laser, and the signal recorded in spectrum is just the emission of the gas cloud. So for the inverse function mode, the G1 cannot learn, have never learned such kind of knowledge, and it cannot work well. But with the help of optimization mode, it can converge to a physically reasonable estimation. And you can compare this emission spectrum to the previous absorption spectrum. You can see how different these two tasks are, and this in turn embodies the reconfigurability of the SVPEN. The second case is about the turbofan preliminary design. The turbofan is kind of a mainstream propulsion system in aircraft or civil aircraft now. The task here is to, according to the performance requirements, which I mean is the thrust and fuel consumption, to estimate the design parameters. This is a typical ill-posed problem because we only have 2 inputs, but we have 11 outputs. And in this task, we do not train G1 because we do not know which kind of group of design parameters are suitable to be labels. So we just use the optimization mode to solve this problem by using 2 multi-layer perceptrons. And we also show a case of how to use extended optimization to solve a design problem. If we still have time and you are still interested in that, I will talk more details later. But basically, I write all the information in this preprint so you can check. Okay, let me do a small short discussion and summarize talk today. So as for the name I list here, which word do you think is most important? The physics embedding? No, in fact, it's self-validated, because self-validation is the intrinsic property of the work here. What I mean is most of the people or many people in the community, their opinion for machine learning is that my machine learning model is God or is going to be God. So their focus is to develop all kinds of algorithms to replace the current systems and to reach such a goal. However, for another school of people, their opinion is machine learning is powerful, but it's not trustworthy, so it needs monitored. Although we have all these weapons to play with, the most important thing is to validate the output of machine learning models. So the emphasis of this work is not about machine learning skills. Although we use a lot of skills, the emphasis of work here is about machine learning phase, and we stand for this school of people. So what's the rule of physics embedding? In fact, the physics is just a symbol that most people trust more than machine learning models. However, it doesn't mean physics is necessary. You can replace it by rules or laws, replace it by feelings, intuitions, experience, or even by some more prestige machine learning models, and then just quantify their feedback, quantify their assessment and feedback to the machine learning model you are using. And from this perspective, our work has some similarities to other people's work. For example, in Mayi's work, they emphasize the self-consistency of AI, and in FPD's group's work, they emphasize the interaction between artificial intelligence and human. So what's the rule of the network? Well, the network here just provide a routine to do gradient-based optimization. So one may ask, is it mandatory to do gradient-based optimization? Well, we did a small experiment on the application of the molecular absorption spectroscopy. So here, we do not only use the estimations from state estimator, but we also use the samples from in situ exploration buffer and random walk buffer to be the estimation of states. For the samples from these 2 buffers, you can regard them as gradient plus noise-based optimization or random search, respectively. And we also added a Bayesian optimization here. So after 1,000 experiments, we found Bayesian optimization uses fewest iterations in most of the cases. So it shows that Bayesian works better than gradient-based optimization from one perspective. However, it doesn't mean Bayesian is best or is always perfect, because from another perspective, the time needed for Bayesian optimization is increasing in an exponential way, while the time needed for the gradient-based optimization, what I mean is SVPEN, is almost constant. And what I have noticed here is that there are only two state parameters needed to optimize for this application. But the Bayesian and random search may not good at high-dimensional optimization. A very straightforward evidence is that we won't use Bayesian optimization or random search to train a network. So for a very high dimensional optimization problem, such as EIT reconstruction, we use some design skills. We can let SVPEN to do this task, and the result is pretty decent. And although the optimization process is not as smooth and as perfect as the previous cases. So if we refer these optimization methods to some Marvel heroes, the Bayesian optimization just like the Hawk, the larger, the stronger, but also slower. Well, the random search just like the Deadpool. So sometimes it's pretty powerful, but you cannot count on that. Or maybe Joker is more purple, but unfortunately he's in another universe, so forget it. And for the gradient-based optimization, we can refer it as Iron Man. At the beginning, it may be very weak, but with the self-optimization inside, it can become a very powerful weapon. So the problem that we need to tackle in future is how to make our Iron Man evolve faster and more powerful. This is a problem related to the optimization error or optimization expense. And the second problem that we need to tackle is we can use an ensemble of optimization methods, but how to coordinate them to contract an effective revenger team. Now let me summarize the talk today. SVPEN is a general framework for solving inverse problems, and it has two modes. Inverse function mode gives the first efficient estimation, and optimization mode leads the way to solve the problem iteratively. So all estimations have to go through the validation provided by the physical fault model inside. Thus, we can assure the acceptable results are physically reasonable. Last, SVPEN bridges between data-driven and physics-driven models, which solids the foundation that using physics-driven models under the context of AI. Well, this phrase I added just before I entered the seminar, that when asked what good is electromagnetic induction, Faraday replied, what good is a newborn baby? So as another newborn baby, we do believe that SVPEN is perfect and it has a long journey to develop. And the most important information about this talk today is not about machine learning skills or the algorithm. The most important information we want to offer is a set that view machine learning from another perspective. So if we deliver this information in a proper way, we'll be very glad. And if you already have this perspective, we will also be very glad that we provide you some, support materials. Last, I want to end today's talk with two quotes from the philosophers from China and Greece. We are respectively my hometown and my supervised hometown. The first one is from Lao Tzu, Dao De Jing. He said, everything has two opposite sides, yin and yang. The interaction between both creates an eternal harmony. So the yang here can represent forward process, physics, etc. The yin here can represent the inverse process, artificial intelligence, etc. The second one is from Aristotle. He said, Plato is dear to me, but dearer still is truth. The Plato here is artificial intelligence. The truth that we believe more is physics, rules, etc. That's all. Thank you.
Thank you, Ruiyuan. Could you go back to the slide where you show the schematic of your SVPEN. I think in the first few slides where you show the whole structure,
Okay.
the error estimate network, the network.
Yeah. I see.
Oh yeah, this one. And then, yeah, okay, this one. So my question is, so I think I already mentioned this, but I want to make sure that I understand it correctly. That so here the physics forward model is expensive. Sometimes is involved with interacting with the environment. That's why you mentioned reinforcement learning, and this it cannot backpropagate through this F. That's why you need this error estimator to
exactly.
update. Okay.
Yeah, exactly.
So, So I was confused that if this one is a surrogate, is another neural network or just a function, then you can use this structure to, update the parameters of the state estimator. But because this one is really expensive to evaluate, to compute, and it's impossible to do backpropagation, so you need other stuff.
Yeah, exactly.
Oh, yeah. Thank you. Yeah, I think that's the most. The hardest part of this whole universe problem.
Yeah,
right?
Exactly. Yeah.
Great.
Thank
you.
Yeah,
thank you, Ruiyuan. Yeah. Do we have any questions for our speaker? Okay. Yeah. Thank you, Ruiyuan, again, and Dimitrios for your talk today. And
thank you.
Yeah.
Thank you for having us, Zongren, and please pass my best to George.
Sure. Yeah, we'll update the recording of this today's two talks to YouTube, and you'll see by searching Crunch Group on YouTube. Yeah, we're uploading seminar recordings of seminar to the YouTube channel.
Fantastic. Send us the link. Send Ruiyuan the link. I'll be looking forward to it.
Yeah. Thanks. Okay, so this is it for this week's Crunch seminar. Everyone has a good weekend. Yeah. See you. Bye.
See you. Bye-bye. Thank you. Bye-bye.